today. I'm Ashwani, and today I'm going to talk about the shielding work that we have been doing for some time, and then how we use this work to shield some learned policies. So let's get started. I am the talk is very lightweight, so if at some point you need more details, you can stop me and ask questions if you don't understand something. Yeah. Okay. So in today's talk, we will see how we actually got from this left-hand side where the rover doesn't land on the helipad to the right-hand side where the rover lands at the helipad. So this will be the final thing we'll see today, and the talk will be about how we achieve this. Okay. So now we have AI and machine learning in everything from your television, your car, to even rocket launching. Now, when these applications are simple, like in your TV, some testing is fine, and you can deploy your product and be fine with it. But if it is really very critical, you really need some guarantees that the system will work fine when you deploy it. So this is what we will try to do. We will try to give guarantees on our learned systems of satisfying some qualitative properties. So let's start with a very simple example. Let's say you have sent a rover to Mars, and there is a solar farm where the rover can go and get charged. There is a remote station where it can send messages to Earth. And the rover is trained to navigate in the Martian landscape and keep the battery charged when it moves around. So let's say there are different paths from the solar farm to the remote station. One is a very simple path which has no obstruction. You can easily go from the solar farm to the remote station and back. There is another path which has a bridge, and the bridge is very old and it may fall, and there might be an accident. There is a chance of accident every time you cross. Okay, another path is a path through where other rovers travel and they collect resources, deposit, and so on. So in this path, you'll find traffic, but maybe some other rovers are free, so they can give this rover a lift. So you might actually save some energy. But during traffic, you may lose a lot of battery. There is another path which is really, really bad, and you really lose a lot of battery. You will reach the other side, but it will drain the battery a lot. Now, the rover is trained to navigate here and take one of these paths to go from one side to other while keeping the battery charged. Now, what we want to do is to force the rover to actually also keep going to the remote station, because the rover might cheat and might just stay at the solar farm if you ask it to keep the battery charged. So we also want to add this constraint that it has to again and again go to the remote station and relay messages back to Earth. So the topic of today's talk is how we can enforce additional quantitative requirements on our learned systems in an online fashion. And this work has been accepted at AMAS 26, so you are getting the first view of how this works. Okay, so let's get started. So I will briefly give the objects we are working with very simply. I won't give formal definitions. Here we have a Markov decision processor. Most of you already probably know about this. Here we have some states. We have on each state some actions, and then there are some stochastic nodes where it decides non-deterministically where it will go, or basically with some probability it decides which state you will end up in the next step. And there is a reward on each of these transitions. And basically, this Markov decision process models the Mars rover example we just saw. So we want to build a policy to maximize the average reward on this Markov decision process starting from an initial node. And a policy for us is just a distribution over actions. So something like, let's say it says at V1, you choose action A with probability 0.7, B, C, D with 0.1. With probability 0, you pick E. That's a policy. And you have this distribution for all these states, right? And that whole thing is a policy, right? And we want to, again, maximize the average reward while visiting V5 infinitely often, the remote station. You want to visit that infinitely often, right? So you might ask, okay, why don't we just train for this? We can just take the reward that we get and also add the qualitative property and just train models for this. The problem there is that with qualitative specifications, we have sparse reward. So that means that you will get reward when the specification is satisfied. And even when you get a reward, you don't know which action in this long run helped you get this reward. So you can't really learn what is helping you and what is not. Okay, somehow let's say you can deal with this. The problem is still that you will have difficulty getting sure or almost sure guarantee that, okay, you will satisfy the specification, right? Surely or almost surely. Another thing is that, okay, again, if you manage to deal with the first two, the problem is you will have to retrain your model if the specification changes, right? So maybe right now you have to go to the station infinitely often. Maybe the station moves away somewhere else, and now you have to go there infinitely often. Or you have there is another area that you have to visit again and again. Another specification is added on top of this. So every time the specification changes, you have to retrain, and training is usually very costly. Okay.
Question, Ashwani.
Yeah.
Sorry. So maybe a naive question. So when you say train, what do you mean? Is it a reinforcement learning or some other?
Choose your favorite way of training. Like you have data and get a policy somehow, right? Like that's what I'm calling training. Like RL is one good example. Yeah. But anyway of deciding how to take the next action.
Thanks.
Right. So you will have from the data, you get this policy. So this is extremely costly no matter what you try. Okay. So in our work, what we propose is using a shield for this purpose. So I will explain now what a shield is. Then I will tell you how to construct this shield. Then finally, we'll see how to use this shield for our purposes. So let's get started with the shield. So shield is nothing but just a layer between your trained policy and the actual MDP. So what this means is when the policy says that, okay, you should take an action A, it goes first to the shield instead of directly to the MDP. Let's say you take an action A, the shield will check whether it is compliant to a specification. And if it is compliant, then it will send this action to the MDP, and then we will move in this MDP. If it is not compliant, then you can either ask it to change the next action, or you can yourself modify the action and then send it to the MDP. Okay, so the shield basically sits in between the policy and the MDP, and then it will check, monitor, and pass on the action if it is compliant with the specification. Now, what you can also do is that now, if you want to satisfy another specification, you can just put in another shield instead of just changing the policy. You just put another shield in the middle, and then you can now monitor and evaluate for this new specification. What this allows us to do is to decouple the quantitative part and the qualitative part of our
Ashwani,
problem. Yeah.
so this shield is only based on the states of the NDP, or it's also on the environment as well? So does it know what's
So,
look at
so
environment variables also, or what?
So the shield has access to the MDP as well, the structure, not the probability distribution, just the structure, what transitions are possible and what are not. Right. So it only sees the MDP. That's it.
Okay. Okay.
Yeah. And the specification that we have is also on the states of the MDP, right? So you might say visit this node infinitely often, or add other parity constraints or whatever on this MDP.
Mm.
Okay, good. So now this is what we propose, and this allows us to decouple the quantitative part and the qualitative part of our problem. Now, shielding is a bit difficult in general, right? So safety shielding is easy. So if your specification only says always be safe, then it's easy, because if an action that is proposed by the policy is going to lead you to a bad state, you can then just stop and say, okay, now this will violate the specification, so this won't be allowed, and you can move on. But liveness is difficult. You can imagine why, because every time you take an action, like with a finite trace, you cannot conclude whether the policy is intending to satisfy the liveness property or not. So even if it is taking some good actions now, maybe it won't take good actions later. So you can't basically just say, yeah, it is satisfying the liveness property. Another thing that we have to be very careful about is that the shield should not interfere too much with the trained policy, right? So the policy we have built for a reason, because we had data about the quantitative part, and we built this. Now, if you just put a shield and just force it always, which forces always to satisfy the qualitative part, then it's just bad, because now you are losing on the quantity, the average reward that you were going to get, right? So it should not interfere too much. It should only interfere when needed. So because of these two, this shielding is very difficult. Now, in this work, we actually show how we can build a liveness shield for our purposes. So as far as we know, this is the first work which provides a liveness shield. Okay, so now how do we construct this said shield that I just mentioned? Okay, so for this, what we do is we turn to games and graphs, where we have two players and we play for the circle player. So the circle player wins if the specification is satisfied. The triangle player wins if the circle player fails in satisfying the specification, right? So this becomes a game between two players, one like the system and the other the chance player. And we want to find a strategy to infinitely often visit the node V5. Okay, now there are many ways of coming up with with a winning strategy for such games, right? So these are solved problems. Now, the problem with these current techniques is that it will give you one winning strategy. Let's say it will say, okay, take this edge E always at V1. Well, this is a very good winning strategy, but now it does not work well with the reward structure. So if you remember, like the reward of E was 0. If you didn't remember, it's fine. So the reward you would get taking the edge E was 0. So this is a really bad situation because you want to take action E because that's a winning strategy that you got from your solver, but now you cannot take it. I mean, you will just lose a lot of reward, right? So just one strategy is not good enough. The problem in the other extreme is that there might be infinitely many winning strategies, right? Here, for example, you can alternate between D and E. You can take D 10 times and then take E 500 times or whatever. So there might be infinitely many strategies. So you also need to somehow have a data structure that can represent all these infinitely many winning strategies. So what we basically do is we come up with something called strategy templates. So strategy templates don't give one particular strategy. They are like guidelines that you should follow uh, to actually satisfy the specification. So for example, here notice that if you take, first of all, if you take C, then there is a chance that you may end up in the losing state V2, right? And you will always be stuck there. So you should never take this edge, right? If you want to satisfy your specification, right? So this is one guideline. So every time we take an action at V1, we have to ensure that we do not take action C. Another thing we have to do is that, okay, to go towards V5, we have to ensure that we actually take one of these edges, B, D, or E infinitely often, which means that, okay, don't get stuck in this A loop, right? So don't always take A. Ensure that you infinitely often take B, D, and E. So these are two guidelines that we have to visit V5 infinitely often. The first thing we call is a safety template that never take an action which is bad. Another live group template which says from this set of edges, take at least one infinitely often. Right? So if you follow these two guidelines, no matter how you choose your actions at V1, as long as you satisfy these two rules, you will always
Ashwani,
satisfy.
question.
Yeah.
So this, how can you take B, D, or E infinitely often? I mean, you can take it only once, right?
So there was to remove clutter, I removed the back edges.
Okay.
So it's a two-way thing. So from V5 you can also go back, but from V2 you cannot. So it was in an
Okay.
earlier diagram. I just removed it to remove clutter.
Okay. And
But
the
Mhm.
stochastic nodes actually have some probabilities on the outgoing edges, is it?
Yeah.
Okay.
Yeah. And also, even if let's say there was not not no backage, basically this live group template says that if you come to V1 infinitely often, you have to keep taking B, D, or E, which means that it basically rules out the possibility of taking A infinitely often, always, right?
Right.
But yeah, there are packages. Yeah, I should have mentioned this earlier. So thank you. Okay, so if you follow these rules, you will end up satisfying your specification. In earlier paper, we showed that if you can satisfy these templates, you are guaranteed to win the game. And uh, you can compute these templates uh, like for any omega regular specification kind of efficiently. Efficiently here means in the same time you would compute for like in the same time the best algorithms work, like the current based algorithms work, right? So quasi polynomial for parity and so on. Okay, so you do not basically spend unnecessary amount of time to get these templates. And you might have noticed that it took this global specification of visiting V5 infinitely often and decomposed it into local specifications, which you can satisfy when you are at a particular node. So at V1, you can decide what to do because you have to only take into account two rules. One, never take C, another take B, D, or E again and again.
So Ashwani, how is this different from a normal strategy?
So a normal strategy will only tell you take E. So a strategy, like if you use standard solvers, it will give you one strategy, which says take action E at V1 or take action B at V1. What we gave is a template. So now you are free to at runtime choose whether you want to take B right now, D right now, or E right now. You can even take A if you want. So you can take A 5,000 times, 10,000 times. I don't care. As long as at some point you take either B, D, or E. So it allows you to choose your particular strategy at runtime. Right? I'm not saying, okay, always take just E or take D and E and D and E and D and E. Right?
Okay. So that's kind of rephrasing the specification itself in a way, right?
Exactly.
Okay.
So we rephrase this global
In a more local way.
Yeah, exactly. This is the point of this, right? So we now at V1 we can decide what to do, and at every node you get specific like local specification like this, and if you keep satisfying them always, you will end up satisfying the global specification we started with.
Actually, question.
Yeah.
So don't you get dependencies in the sense that if you do something at V1, then you should do something at V5? These are like sort of memoryless templates.
Yeah. So that's a very good point. So we show that for omega regular specifications, this is enough, right? So if you have, okay, I lied a bit here. One more thing is needed, which is co-live template. It says do not take an edge infinitely often. So it's kind of dual of live. So it says you can take this edge finitely often, like for Kobuki type of things. It says take this finitely often. After this, you are not allowed to take this, right? So yeah, basically, if you have these three things, you can decompose a omega regular specification. You get a template. Satisfy the template, you will win the game. Now, here's the catch. Because of what you just said, uh, it's not complete in the sense that it does not capture all the winning strategies. It captures infinitely many, but it does not capture all. But it does capture all the winning plays.
I see.
Right? But for us, it's enough to have infinitely many strategies for all practical purposes. We never found an issue where like we needed to use this approach and this strategy is not available.
But does it capture all memoryless winning strategies?
Yes, it does capture all memory listening strategies. Yeah. So the strategies it does not capture are the ones where somehow the environment decides to become really friendly. Right. So sometimes those kind of strategies are missed, but memoryless, we capture all of them.
Yes.
Yeah. Okay. So, yeah, right. So we have these strategy templates. Now, how do we use the strategy templates to build, like use as shield? So what we do here is the following. Let's say you have a trained policy which says, okay, take A 0.7 with 0.7 probability, B, C, D with 0.1. E you should never take because it's just bad for the reward and A is good. Okay, what the shield does is the following. It first picks a small alpha, let's say 0.05. You can pick, like whoever is actually deploying the system can pick. Here we'll pick 0.05. What it does is the following. At V1, when you come at V1, first we ensure that the unsafe actions have 0 probability. So C becomes 0. You never take that action. Then you normalize this distribution, and then you sample from this distribution. Now, let's say like you are for sure guaranteed that you will never sample a C because probability of C is 0. Now, let's say you sampled a 1. Okay, I think there is a typo here. B and C have been switched. Sorry. Right, so now what happens is if you sample A, since it was not part of our live group said you should take B, D, or E, we will nudge the probability of taking B, D, or E next time. Right, so this means that with this small alpha here, we will increment probability of B, D, and E, right? So, and then normalize. So now you notice that from 0.7, probability of A has now become 0.66, and B, D, and E have gained some chance of being chosen. Let's say you still sample A, you again increment, and you keep doing this, and you will realize that chance of picking now B, D, and E is increasing. Eventually, the probabilities will change such that the live edges, B, D, or E, are really favorable. So at some point, you are guaranteed to sample B, D, or E. And when you sample, let's say B, then you will reset the probabilities of B, D, and E, and then continue sampling. Right. So with this alpha, we call enforcement parameter. What we do is every time you do not satisfy the live group template, we add some probability to those edges so that you are eventually kind of forced to take this. So this we are not saying take B, D, or E now. We are letting you do A sometimes, but at some point you are kind of forced to choose B, D, or E, right? And this will ensure that you satisfy this specification. So we show that using this technique, you can surely or almost surely, depending on what you want, satisfy your specification. It also interferes minimally. Like if you keep the enforcement parameter alpha very low, you can almost simulate the original policy. I can give more details about this later, but we show that if you want to be very close to your reward, you can actually get there and we won't interfere too much. Right, so this is what we said. So you can get epsilon close to your original policy's expected reward. So it really interferes minimally. And it is also compositional. And this property just comes from compositionality of strategy template. So you can now add more specifications on top of your qualitative specification that you started with on the fly. You just have to again compute templates, compose the templates. It is very simple, and then just keep nudging the probabilities with the new template. And you can do all of this online. You don't have to stop your system even for like a bit. Yeah? So you just continue doing this. So what we did was we took all of this, implemented a tool, and then built a benchmark of these factory grid worlds. And here what we did was, here if you see, we have some cells with reward 1. We want to maximize our average reward, right? So if you want to actually visit here a lot, right, to maximize your reward. And this green cells here are the view key region which you want to visit infinitely often. That's the qualitative property. So if you take your learned policy, it stays in this one region, right? Now, at some point, let me move it a bit. So we activate the shield. And here we have enforcement parameter, which is very low. So when it's low, it goes to the green region very few times, and it stays in this one region a lot. If you increase the uh, enforcement parameter, then it will actually start staying in the green region more, and then it will go get more reward once in a while. And where's yeah, and online you can also add this new view key region. So here, this is the green cell that we added online. So there are two objectives now. Satisfy this, basically visit this big view key region infinitely often, and this other green cell infinitely often. And without stopping, we can continue satisfying both of them, right? So you can just compose the templates, and you will now see that it goes to both green regions and also gets the reward. Okay, so you can also play with this at mark.mpisws.org. Don't go there now. Stay with me for a bit, and you can try that. So when you don't have a shield, so this is a heat map. It shows that the bot actually stays in this one region just to maximize the reward. If you have very low enforcement parameter, which is like you don't nudge the probabilities too much, it still stays in this region a lot. Once in a while, it goes to the green region. And if you increase the enforcement parameter really a lot, then it will visit this green region more often. Right, so you are kind of losing reward, but you're satisfying your specification more often, right? So the point of showing this is that you can now tune uh, how much you want to satisfy the specification, right? So if there is no real need to actually go to the green region, you can just chill, gain the reward. If at some point you really need to satisfy your specification, you can crank up the enforcement parameter. You will start satisfying the specification. And then you can again uh, collect reward by reducing the enforcement parameter. As long as you keep the alpha greater than 0, strictly greater than 0, you are guaranteed to visit the uh, green region infinitely often. Not like you are guaranteed to satisfy the specification as long as alpha is greater than 0. And then you can tune whatever value you want to pick for alpha. So what this graph shows is that when you increase the enforcement parameter, frequency of visiting goal state increases, but the distance from optimal reward also increases. So you get far away from your optimal reward. Now, okay, so far we saw that, okay, if we know MDP, we can solve all these games, get the template, and then build a shield. But usually in real life scenarios, we do not have the MDP. For example, this benchmark from the gymnasium benchmark, the lunar lander, it has 8-dimensional continuous space, and we don't know the underlying MDP. I mean, the dynamics are there, but still the MDP is unknown. So for these kind of problems, what do? We first take our environment, we discretize the space. So what we did here in this particular environment was we discretized the space with just the first two dimensions, which was the x and y coordinate. We totally ignored the angular velocity, the velocity, and two other dimensions. We just took the x and y coordinate and discretized the space based on that. Then we built the game out of it. It's a very terrible game graph where we say if the engine is not fired, you will go to the cell below. If the left engine is fired, you will go to the right cell. If the right engine is fired, you'll go to the left cell. Very, very basic abstraction. And then we built the shield on this. Here we wanted the uh, rover to visit the blue region infinitely often, right? And then we got the template, and then just used that same template on this continuous 8-dimensional space. And we saw that even with such very crude discretization and abstraction, we are still able to make the rover land. So here, since we are not bothering the learned policy, which was trained to just land safely, we are still able to, with just 2 dimensions, land safely and on the helipad. Right? So you will see that now it will land on the helipad.
So
Okay.
why couldn't you just give a safety
Oh,
requirement there?
that's a very good point. So I was going to comment on this later, but here, let's say the orange region you see, we also tried another experiment where we put the orange region to be the unsafe region, right? What ended up happening was the rover didn't know where exactly it has to go, so it would just hover and not go in this orange region. But that doesn't mean that it will actually go to the helipad. It just hovered, and eventually it would time out and it wouldn't even land. Right? So, say with safety specification, you can. I mean, it didn't land many times. It would just hover, but with our liveness specification, which just says stay in this region, kind of. Since it's targeted, it takes the rover towards the helipad. So that's the difference. Did I answer your question?
Okay, so you're saying that it doesn't have a target, but wouldn't
Yeah.
the policy already have that? I mean, the
That's,
RL policy would.
yeah. So the RL policy, let's say here. So RL policy says just land safely. Let's say you're. Can you see my mouse pointer? Okay, I think
Yeah,
yeah.
yeah.
So let's say somehow the rover ended up here. Okay, in this region. Now what happens is the rover is trying to go down, but the shield is forcing it upwards, because this is unsafe, so you have to go up. Now the training is saying go down, the shield is saying go up. So it has to it cannot do much more than just hovering over here. Right? So that's why it used to get stuck a lot in these regions. And then it wouldn't find a way to actually land. And then again, it would time out. Maybe if you let it run for like, I don't know, forever, even then there is no guarantee that it will actually land, because you can imagine a scenario, really, right, that the training says go down and land here, but this shield says you can't land here, and then you don't know what to do.
And if the same thing happened with the infinitely often shield, then I mean, why doesn't that happen?
So it doesn't happen because, like we said, infinitely often see this blue region, right? So now what it does is, like, when it is trying to, let's say, go, so the training says go downwards, right? And it, let's say, tries to go too far away, then our shield nudges it back to the blue region, right? And then training says, okay, keep going down. And then our shield keeps bringing it back to the blue region. So it ends up landing in the helipad, right? Because we are not letting the shield, the liveness shield is kind of nudging it towards the goal. So it's more targeted.
Ashwani,
Mhm.
so here the training is assumed to only move it downward, is it? But
Not downwards, but just land safely,
but
right?
doesn't it like what I'm seeing is the training and the shield are orthogonal here. Training is only working with the vertical axis and y-axis, and the shield is only working taking care of the x-axis, right?
No, I mean, that's also, I mean, so in this particular example, the shield kind of only cares about the x-axis, but the training cares about all 8 dimensions, because when we trained, it had all the information. It was only trained to land safely. So now maybe because of the wind, somehow it feels okay, going this way is better, right? So during the training, maybe it learned that this path is really good if the wind is high. But then uh, our shield, what it does right now is that it sends it towards the blue region, right? So the training will try to go here, downwards here in this, follow this path, but the training will bring it back here. So like you can imagine, like when you see the video again, right? So you see it tries to go away, but then it comes back. It tries to go away, it then comes back. So because of this, it just ends up landing in the helipad.
But doesn't the RL policy also will take care of moving to the closer to the final target location in the
No, 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 no. Because, okay, yes, so it was not trained to land on the helipad. It was just trained to land, right? So because in the original environment, there is a fixed helipad. But what we did was generate the helipad arbitrarily, which means helipad sometimes could be here, sometimes could be here, sometimes could be here. So if if it is at a fixed place, you can train to land there. But if it is not, during training, you don't know where it will be, and you don't have a way of knowing that. So you cannot really train to land on the helipad.
okay.
So, but here,
So in
yeah,
this case, the policy has been trained only to land safely, like it does
safely,
not track
exactly.
the. Okay.
Exactly, just land safely. So remember, we decoupled two things there, right? So here we decoupled the specification like this. So we took landing safely part and we just trained for that. And then landing on the helipad, we built shield for that. Right? So, and then together we see that it lands safely on the helipad. Right?
Um, did you compare any with a fixed helipad location? Does the RL policy itself, how does it like?
So, for the fixed location, the RL policy, yeah, does well. I mean, you can train it. There are really good ways of training it to actually land on the helipad. Like you will really, really land most of the times on the helipad. You can do that. Uh, but if the helipad keeps changing, you don't know where it will spawn, then you cannot. I mean, then it doesn't work.
Okay, thanks.
Yeah.
Yeah, thanks.
Because you realize whether you landed on the helipad only when you have already landed. And as soon as you land, the environment is gone, right? So you have to stop. And then you cannot actually correct and go and land somewhere else. So if the helipad spawns at random positions, you cannot train for this. I mean, at least in the most obvious ways.
Okay.
Yeah. Okay. So
Sorry, can I ask a question also? So that's
yeah,
a
yeah.
very cool slide. So I mean, I don't think people don't want to move away from this slide. But like no. So I mean, are you saying that it is? I mean, it is possible to put extra effort and train it to land. Train it to not move away from that blue line.
Mhm.
And instead, you're saying that maybe you can decompose the training as do a smaller train it for a smaller thing and use a shield
Mhm.
so that the final goal is achieved. Is that
Yes. Yeah, yeah, yeah. Exactly. So also here, when so in this example here, right? So when you just don't put a shield, you see it just like tries to go down, but it's not fast enough. It's just trying to land somewhere, right? And at the cutoff time, it does not land. It is still hovering. Maybe it will go like it is. See, you see, it was actually trying to. Oh, why is it laggy? So you see, it started from here and it was actually following this path to land. Right? It was going to land, but at the cutoff time, it didn't land. But if you put our shield, then it lands much faster because we are keeping like making it targeted, right? So it does not have to aimlessly wander here or there, right? So it ends up landing faster.
Okay.
Right? Now, what happens if you actually increase the alpha, like the enforcement parameter, then you see that, I mean, it forces, oh, let me pause these two there. Yeah. So it forces it too much. The shield forces it too much to follow the to stay close to the blue line that you see, that it sometimes topples or tries to topple, right? Because we have totally ignored angular velocity and velocity. So but the training is good enough to actually save it from just crashing. So you see, when you increase alpha, it is like violently forcing it to stay close to the blue region. But then with training, it lands. If you increase it too much, it will for sure crash because the training is not done for protecting it from like extreme situations. Okay, so what we saw in these experiments was that when we use our liveness shield, we ended up landing in 90% of the cases at the cutoff time, right? So if we let it run for longer duration, it will land more. But for safety shield that I just explained earlier, right? For safety shield, it only landed around 36% times. And when you don't use shield at all, it landed like 10% time.
So,
Now,
Ashwini, did you try a bounded safety? Like, I don't know whether that's like bounded liveness, which is a safety condition. I mean, get to this
right.
point within so many steps. So
Actually, we did not try this.
that would be like a safety property, right?
Yeah,
Kind
that
of
would be, yeah. But then my guess would be that like, you would say, okay, get close to this, let's say blue region, or land within like uh 10,000 like time steps, and then the problem will be the graph will be too big or something. So I'm just guessing. I don't know. So there might be problem, more computational cost maybe. Yeah. So I don't know. We didn't try. So it's a fair point. Maybe we can see what happens. But yeah, honestly, we didn't try. Okay. Also, what we saw here was that since we are targeting towards the helipad, we also end up landing faster. So the cutoff duration was actually 10,000 time steps, and on an average, we landed within 5,000 time steps without the liveness part, only just safety shield. It took longer to land whenever it landed, right? So basically it was hovering. At some point, if it came just above the helipad, it could land, but it takes longer duration to land. And if you don't have a shield, it still takes longer than our liveness shield. Yeah, so yeah, that's all I have for you today, and I'll be happy to answer other questions if you have. And feel free to also contact me if you want to know more details about this, or like in-depth detail that I ignored here. Yeah.
Thank you, Ashwani. Are there any questions for the speaker?
Yeah.
I had a yeah. Go ahead. Go ahead.
Yeah. So the compositionality of multiple shields, right? So does that mean you can build separate shields and cascade them?
Yeah, so basically what that means is you have multiple templates or like shield. You merge them together to get one shield. So basically let's assume that your specification says, so let me go back to the graph, maybe then I can, so maybe the, come on, go back. Okay, it crashed. So for example, here, let's say somehow maybe your specification also says there is another edge, let's say X here going out, and your specification, like another specification comes and somehow says that you have to visit this node infinitely often. So you take this X edge infinitely often. What this basically means is like you can compose these two and you can just say that infinite, when you are deciding what to take at V1, you have to now satisfy both of these rules. You have to ensure that you take B, D, E infinitely often and this X edge infinitely often, right? So you can now alternate between X and B or X or D and so on. So you have to now satisfy just more constraints. That's it. So the composition is extremely simple. And if some edge like B becomes unsafe, you just drop it from this live group. You still have D and E to take infinitely often, right? So you just compose these rules with very simple logic, and then you are good to go. You can just use the new set of guidelines to nudge your probabilities.
Okay.
Right. So, yeah. So the composition is very, very simple, and it's extremely powerful. That work we did in another paper for strategy templates, and we saw that we could compose multiple objectives online really well. We could satisfy multiple specifications at the same time without stopping our previous computation. So we do not waste a lot of resources solving the game from scratch and so on. Yeah.
Okay. Thank you.
Any other questions?
Yeah. Hi. Thanks for the talk. I had a small question regarding this the continuous setting. So you had this example where when you have high alpha, there's kind of this overcorrection and then it swings and oscillates, right? So,
Mhm.
I mean, what I'm thinking is, to what extent will this specification be satisfied? Is that somehow dependent on how you design the discretization and how you do the abstraction? Could it be that there is some continuous setting where, because of the choices you made in the abstraction, the shield that you learn on the abstract MDP is actually not good enough to ensure that your specification always gets satisfied? Like, is that a possibility or?
Yeah. Totally, right.
Uh,
So, for
uh-huh.
example, let's say I my abstraction was only, let's say, x coordinate and angular velocity, right? So in that case, I don't think we will ever be able to guarantee that we'll land, right? So basically, it really depends on how you build the abstraction. But the point is that here we pick two most relevant part of the state space, which is x and y coordinate. And even with a very, very, very bad abstraction, like extremely bad abstraction, this was very basic, we are still able to get very good results. So if your abstraction becomes better, let's say you take into account other dimensions, and then discretize based on that. And you have better edges, like not like, okay, if the engine is fired, the right engine is fired, you are guaranteed to just go to the next left cell. You may go to third next left cell, and so on. So if you build better refinement and like the better abstraction, you are for sure guaranteed to get more out of this shield. And if the abstraction is bad, yeah, you cannot say anything. Okay.
I
So
see.
it
Okay.
is dependent on abstraction, and people who are building the system are expected to kind of know their domain and then build the abstraction based on this. It's like, yeah.
I see. I see. And I guess, I mean, is it like kind of, I guess the question of whether or not like any given abstraction is good enough is something that is like a completely separate domain specific question from your point of view,
Yeah.
right? Yeah.
Yeah. And there are like many works on this thing, right? In robotics, for example, they use abstraction-based control design things, right, where they actually build the abstraction from what they already know about the dynamics and then use that to do whatever, right? So this is a big area of research of how to actually get better and better abstractions.
I see.
Yeah.
Okay, thanks. Yeah. Also very, very nice slides. Thanks a lot. Yeah.
Thank you.
Any other questions for Ashwani?
Yeah, I have one more question, Ashwani. So,
Mhm.
uh, uh, is can RL algorithms be adapted to learn a strategy template instead of a policy?
Yeah, so that's a very good point. And this is something that we are actually working on, and then we are going to submit it soon. So, yeah, what we did was, so this is post shielding, right? So once you get the RL policy, you can shield later the policy. The main goal here for us was that, okay, if we want to change the specification, it should not be too difficult, like too time consuming. But let's say somehow you know that your specification is not going to change. Can you guide the learning so that it converges fast and also satisfies the specification? So this is pre-shielding, and this is what we are actually doing right now.
Oh,